Recording now. Good evening, everyone. So let's continue our example from last time, right? So we reached until step 14, right? So the step 14, which we haven't completed yet, is to expand the pseudonode. And the reason was that we couldn't do any of the previous steps. So of course, this is our only choice, right? Okay. Are there any questions or concerns until this point in the algorithm? Is everything fine? Yeah. Okay, great. Okay, so let's do step 14 here itself. I will erase these TIYs. They're already on Piazza. So we want to expand the pseudonode. So the vertex Q, the node Q, it corresponded to 5 vertices in our original graph, right? So I'm going to redraw those 5 vertices. Okay, so that's V0, V1, V2, V3, V4. And this was a set vertices of the cycle or cycle Q, right? And we want to redraw these edges. Okay, so the complement looks like this, these 3 vertices, and these 3 edges correspond to edges joining the odd cycle in this triangle. And those 3 edges look like this. If you go back to the original graph, you can see that those were the 3 edges. And one way to keep track of this is to give labels to the edges, right? So this edge, if you remember, we had actually labeled it as V3, V5. So that would correspond to V3, V5 here. And yeah, and this one was V4, V5. Okay, this is the vertex V6, this is the vertex V7. Okay, so we are expanding the pseudonode. So we had this instance G prime, C prime, right? So we want to make sure that we have the costs updated accordingly. So let's see. So the things that are already the same, let's just put them down first. So this is 6, this is 8, this is 9. And the dual variables also, the ones that are in the complement, so outside the vertex Q, those are going to remain the same. So let me put them. This is a plus 2.5. This is a plus 1. This is a plus 3.5. Right? Okay. Now the edges of the cycle Q that are like both the ends are in the vertices of Q, those the cost will be the original costs, right? So what were the original costs? There were 2, 3, 4, 4, and 4, right? And also let's put down, okay, so these costs I've already included. Okay. And now we need to figure out the dual variables and the costs of the edges joining the vertices of Q to the complement V5, V6, V7, right? So those are going to be updated exactly how we updated when we went to C prime, when we shrunk the blossom, right? So if you remember, when we shrunk the blossom, we subtracted the y bar value for the vertex that was in the blossom from the original cost. So now we are just going to add that back, right? So in fact, let me first put down the dual variables that we had earlier. So maybe let's go to a previous page to see what we had, just so that, okay. So when did we shrink the blossom? We shrunk it at step 8. And prior to that, we had these dual variables. So we're going to put the dual variables as we had them earlier. We basically store them. We don't discard them, right? So they are going to be plus 1.5, plus 0.5, and so on in this circular fashion. So let me just put them down first in red. So that's a plus 1.5, plus 0.5. Okay. Plus 2.5, plus 1.5, and plus 2.5. All right, and now we need to figure out the costs of these edges. They are going to be the costs we have in the previous instance, plus we will add the dual variable corresponding to the end of that edge in the vertex set Q. So this 3.5 here will become a 3.5 plus 2.5 back to 6, which was our original cost actually. But the reason I'm doing it explicitly is because you could have done multiple shrinkings and then it would not go back to the original cost necessarily. Right here we did one shrinking and now we are unshrinking the same blossom later. So that's why we are going back to the original costs. So this 2.5 here adds to 1.5 and becomes a 4, and this 3.5 adds to 1.5 and becomes a 5. Yeah. All right. So that is our expansion of the pseudonode. All right. What else do we need to do? Right. So let's look at our matching and let us adjust. We may have to adjust our matching actually. So the edge here, QV5, it actually corresponds to V4, V5, V4, V5, right? The above edge corresponds to V3, V5. So we'll take V4, V5, and now we will extend this matching to the original blossom in the natural fashion because it's an odd cycle and we have matched one vertex. And notice that the matching actually has changed. If you go back to the previous page, the matching we had when we shrunk the blossom was V1, V3, V2, V4. But now this has changed because of what we did in the next steps, right? So that's how the matching updates. It's simply the matching you have, and you extend it to the blossom in the only way possible because it's an odd number of vertices and one vertex has already been matched. Okay, great. Okay, so that's the expansion of the pseudonode. Are there any other things that I am missing? Okay, let's look at the tree. So what does the tree look like? This is a good point actually. So let me mention. So our tree in the previous case was this guy, right? What are these edges? Let me call these edges F and G. So F in this drawing is here and G is here. They happen to be incident on the same vertex in the blossom. It need not have been the case. It's a blossom. You could blow it up and F and G need not be incident at the same vertex when you unshrink the blossom. So in that case, the more general thing to do. So in this case, the tree will remain the same. However, in general, what would happen is you have this edge F and this edge G. So F is the edge coming into the white node that you're expanding, right? So this is a white node you're expanding, that is the edge F, and G is your matching edge, like this, okay? And yeah, observe that the white nodes are always degree 2 nodes in our trees. It is only the black nodes that can have higher degree. Because when you reach a black node, you have reached through a matching edge and you will take all the non-matching edges possibly. So that could have a higher degree. But the white nodes, they only have one incoming edge from the top if you root your tree by putting the root on the top. So there'll be one incoming edge and there'll be one matching edge. So the white nodes are always degree 2, right? So let's say this is the edge F, this is the edge G. When you go back to the blossom, your edge F is like this and your edge G is like this. One of these paths will be an odd length path and one of these paths will be an even length path. You take the even length path as your tree. So you include the even length path in the tree and you observe that the tree will still be M alternating or M prime alternating with respect to the updated matching. Right? In this example, because they are incident at the same vertex, the even length path is a zero length path and the odd length path is a whole odd cycle. Right? But in general, this is what the picture would look like. Okay. So in this example, the tree will simply be what it was earlier. You start at V7, you go to V4, and you go to V5 using this matching edge. Okay. All right. Okay, so now we have reached the situation. I also want to make one more comment. You see, why did we choose to unshrink the blossom? Because the pseudonode, its dual variables somehow reached 0 again. We had increased it to something the positive. We always kept it non-negative. And now after doing some changes, it reduced back to 0. Essentially, that means that the corresponding dual variable doesn't matter anymore. That dual variable for the whole set of vertices that corresponds to the odd set constraints of Edmonds, this particular pseudonode, this particular odd cut doesn't matter anymore. We have set its dual variable to 0 once again. Right? So that is a kind of intuition as to why we are expanding this blossom back into its original state, because the dual variable is just it's not relevant anymore. Yeah, makes sense. Okay, good. So now we can continue with the algorithm. We are at step 14, and now let's see what is the next thing we can do. So let me make a copy of this and let's move on to the next page. All right. So this is and just to remind us, V7 to V4 to V5 is our tree. And this is the matching edge in that. Okay. So now let's see what we can do. What are the tight edges? So let's draw the E-tight graph. Okay. So let me just put all the vertices and then we'll figure out the edges. Okay. So I think there is one dual variable missing here. Let me put that in red again. Maybe it wasn't copied. 0.5 here. All right. Okay. So this edge is a tight edge. This edge is tight. This one is also tight. This one is also tight. And this one is also tight. All right. And what about this? This is also tight. Oh yeah, the tree edges will remain tight. That is clear because the tree will continue to remain a tree in the tight graph. And I believe those are all the tight edges. Is that correct? Yeah. Okay. And our tree is this guy, V7 to V4 to V5 with this edge in the matching. Okay. So now let's see what we can do. So in the tight graph, we do have things that we might be able to include in our tree, right? Let's see. So right now, the black nodes are not joining to anybody else. Right. So at this point, we can't grow the tree anymore. We can't grow the matching anymore. We don't have any odd cycle to shrink in our tree. I mean, technically, we could do that. We can consider the edge V5, V7 and shrink that blossom. But let's say we don't do that. Let's say we try to do some other things. Okay. Um, so how about we try a dual update? If we can update the dual, we will do that. Otherwise, we'll have to do one of the other steps. We could shrink the blossom in that case. In fact, sorry, we can't shrink the blossom. Sorry. We can't shrink the blossom because that edge that I just drew is not a tight edge. We would be able to do that if it was a tight edge, but actually we can't even shrink a blossom here. Okay, good. So the only thing we can try is to do a dual update. So step 15 is a DFS update. And let's see what we get. Do we get a beta that is greater than 0? We should. Let's see what happens. So what are the edges we are going to look at? Yeah, so we have this edge, in the original graph, and we have this edge, and we also have this edge. So for the first three edges that I drew, we will take the slack, and for the last one, we'll take the slack divided by 2 because it is joining two black nodes of the tree. Yeah. So let's see what the slack is. The slack here is 6 minus 2.5 minus 2.5, 1. Here it's 6 minus 1 minus 2.5, that is 2.5. And here it is 9 minus 1 minus 3.5 is 4.5. And here it is 8 minus 3.5 minus 2.5 is 2 divided by 2, 1. Okay. And we don't have a beta 3 because a beta 3 only occurs when we have a white pseudonode. But here we don't have any pseudonodes at all in our tree. Okay, great. So we have a beta 1 and beta 2, and we take the minimum which is equal to 1. So beta is 1, and we will increment for the black nodes of the tree, and we'll decrement for the white nodes of the tree. So let me make yet one more copy of this guy. Yeah, let me erase this guy. Okay, and there was one missing label. Let me put that plus 0.5 here. And okay, so now let's make the changes that we decided. Okay, so we will add 1 to plus 3.5. So this guy becomes a plus 4.5. This guy will become a plus 0.5, and this guy will become a plus 3.5. Plus 4.5 plus 0.5, and this will be a plus 3.5. Great. All right. And let's draw the tide graph. I won't redraw. Maybe I'll just modify this guy here. Okay. So, all right. So these edges V0, V1, that remains tight. V1, V3 remains tight. V0, V2 remains tight. V2, V4 is not tight anymore. All right. So this guy is not tight anymore. Notice that 2.5.5 is 3. That's less than 4. This edge of the pentagon joining V3, V4 is also not tight anymore. However, this edge has now become tight, and this edge is tight. This is the vertex V5. All right, and this guy is also tight. Okay, I believe. Oh, and this is also tight now. Okay, let me just quickly check. This is step 15, and that is what it looks like. Yeah, good. Okay, and what is our tree? Our tree hasn't changed. Our tree is still the same. Okay, good. Now the good news is, oh, we have a matching. The matching looks like this here. Yeah. Now the good news is that in the tide graph, we can grow the tree. We can grow it once, and then we can grow it twice. Right? I look at this guy, V3. I will add this V5, V3 and V1, V3 at the same time. Then I will look at V0, and I will add V1, V0 and V0, V2 in the next step. So we have two steps which are basically tree extension. I'll just skip those. Step 16, tree extension, and step 17 is tree extension. Okay, so now our tree is, as I have indicated, using the black white colors, and this edge is not in the tree. at the end of step 17. Okay, good. All right. Now what do we do? Now in the tight graph, we can't extend the tree anymore. We can't extend the matching anymore. We can't augment the matching anymore. Well, we do have an edge in the tight graph joining two black nodes. So we could shrink that into a single pseudonode. So let's do that. So step 18 is once again shrink blossom. Shrink blossom. And this time the blossom is Q1. Okay, so what happens? So our new graph looks the same except that this is now a single vertex Q1. And let's see, how many edges will we have? Okay, so we will have an edge going from V2 into Q1. We will have an edge going from, we will have two edges going from V3 into Q1, one corresponding to V3, V4, and one corresponding to V3, V5. And we will have two edges going from V6 to Q1, one corresponding to V6, V5, and one corresponding to V6, V7. Yep. Okay. And okay, let's put down the costs of the edges, which are not incident at Q1. Those are easy. They are basically the original costs. And let's put down the dual variables as they are in these cases, plus 1.5, plus 0.5, plus 2.5, and a plus 1, and a plus 2.5. Okay. This guy, Q1, what should we put there? 0. We put a plus 0 there. And we need to change the cost of these edges. And maybe one of you can tell me how, oh, maybe I made a mistake somewhere. I think this I should have not done. This I should not have done. Okay. So the edges incident at Q1, those costs we want to compute now. So let me put them in, I don't know, blue color. Okay. So can somebody tell me the cost I should put for this edge? 2.5. It's 4 minus 1.5, 2.5. Okay. What about this edge? 2.5. Okay. What about this edge? 3.5. Right. Exactly. This one? 6 minus 2.5, right? 3.5 again. And finally this one? 9 minus 3.5. Oh, wait. Oh, we should be looking at this drawing. Yeah, we should be checking here, right? Okay, so let's make sure that the numbers are correct. So actually, we made some mistakes. I was also looking at the wrong drawing, sorry. Good. So this will be 4 minus 0.5, so it will be 3.5, right? And then this will be 4 minus 0.5, again 3.5. Okay. I'll draw the edge later. This will be 6 minus 3.5, 2.5. And here we have 6 minus 3.5, 2.5. Yeah, so one has to be kind of careful. I also did this when I was preparing. And now this is 9 minus 4.5, 4.5. So this one is 4.5. Okay, and now let's draw the missing edges. So this is a missing edge, and this is a missing edge. Okay, let me also quickly check my notes so that we don't make any mistakes. 3.5, 3.5, 2.5, 2.5, 4.5. Great. All right. Okay. So that's our current situation. So that is the graph G prime, the current G prime. And what about the matching? Let's draw the matching. Yeah, let me just use dotted lines for that. So the matching will remain as it is, except that the Q edge is basically gone. Notice that the number of exposed nodes is the same. Number of exposed vertices was 2 and it is still 2. Okay, that is something we will always ensure. All right. All right. So what about the tree? The tree is still the same, except that the Q1 has been shrunken to a single vertex. So the tree now looks like this guy is the little Q1. Oh, I think it's supposed to be a white colored. No, wait a second. Oh, did I make a mistake in the colors? Yeah. Okay. Sorry. So yeah, these were supposed to be. Anyways, it doesn't matter. You get the point. I've messed up the colors here. So let me not worry too much about that. The tree is supposed to be um, this single vertex Q1, then goes to V3, then goes to V1. Okay. Again, I'm messing up. V3, V1, V0, and V2. Okay. So that's our tree. Okay. And V3, V1. Yeah. So let me also enable the vertices here. V0, V1, V2, V3, and okay, that's it. So Q1 goes to V3, V1 is the matching edge, and V0, V2 is a matching edge. Okay. What about the tight graph here? So let's draw the tight graph. So V0, V1, V3, V2, Q1, and V6. All right. So what are the tight edges? This guy is tight. This guy is tight. This guy is tight. This guy is not tight anymore. Basically, the tight edges are coming from the previous tight edges. Basically, that's what's going on here. 2.50 adds up to 2.5. So this edge is tight. However, the other edge is not tight, right? And none of the edges here are tight. 0 and 1 don't add up to 2.5 or 4.5. So that is our tight graph, right? So this is what's going on in step 18, right? And the tight graph basically is almost the same as the tree except for the isolated vertex. Okay, so in the tight graph we can't grow the tree anymore, we can't grow the matching, we don't have a odd cycle to shrink, right? So we should try a DFS update, right? All right, step 19. And in fact the only pseudonode which is there is a black pseudonode, right? So we don't even have a white pseudonode, we can't even do the expansion step. So the step 19 is again DFS update. All right, and how do we do this? Let us look at the slacks of these edges. 1, 2. Let us look at the slack divided by 2 of this guy, and that's it, right? Those are the 3 edges we want to look at. Yeah. Okay. So what are they? This guy is 2.5 minus 1 minus 0 is 1.5. This guy is 4.5 minus 1 minus 0 is 3.5. And this guy is 3.5 minus 2.5 minus 0 is 1 divided by 2 is half. So the beta is 0.5. Okay, great. So let's just copy paste and update the beta. Yeah. Oh, sorry. All right. Okay. So what are we doing? We are increasing for the black ones and we are decreasing for the white ones. So let's do that. So this plus 0 becomes a plus 0.5. This plus 0.5 becomes a plus 1. And this plus 2.5 becomes a plus 3. Let me just copy from my notes so that I don't make any mistakes. Oh, right. This is step 19. Okay. So let me know if I'm making any mistakes, but hopefully this is correct. So this is a plus 0.5. This is a plus 3. This should be a plus 1. And this should be a plus 1. And this guy should be plus 2. Is that right? And let me put the missing cost. I think I managed to erase some cost here. So this is 2. Okay, great. All right, so that is our updated dual feasible solution. Yeah, and let's draw the tight graph. So V0, V1 remains tight. So all the edges of the tree, previous edges of the tree will remain tight. And this edge will now become tight because that was where we chose the beta. Okay, and the other edges are not tight yet. So this is V6 and the other vertices are V0, V1, V2, V3, V4. Sorry, bad. That's not the right. This is V2, this is V3, and this is Q1. Okay. So observe that everything is mostly the same. The only thing is we have added one more edge to the tight graph. We still cannot increase the matching. We still cannot grow the tree anymore because the tree is still the same. The only thing we can do at this point is shrinking this blossom, right? So we have one more blossom and we can shrink this. Observe that this blossom looks very much like the first blossom, but it is not the first blossom, right? The 3 vertices have been shrunken into a single vertex, and now this odd cycle in this derived graph is our blossom. So it corresponds to an odd number of vertices in the original graph, but it is not the same blossom that we shrunk earlier. Yeah. Okay, so step 20 is to shrink this blossom. I'll try to finish all the 3 remaining steps in this here in this drawing itself. Let's see. Okay, so shrink blossom Q1. Sorry, Q2. Okay. What does that do? Well, observe that this is basically all the vertices except one vertex. So we're just going to get a single vertex, Q2, and V6 is here. and we have just two edges. The top edge corresponds to V6, V5 from the original graph, and the bottom edge corresponds to V6, V7 from the original graph, right? The yeah, the dual variables are going to be as they were for the blossom will give us 0, right? So this is going to be a +1 from here, and this Q2 is now going to be a +0, right? And we need to modify the costs by subtracting the 0.5 from the two current costs, which is the dual variable for Q1, right? So 2.5 minus 0.5 is a 2, and 4.5 minus 0.5 is a 4. Okay. And what about the matching? What is the matching currently? What is our M prime right now? Nothing, empty, right? Notice that the number of M prime exposed vertices was 2, it is still 2. There are only 2 vertices. Okay. And what about the tree? What is our current tree? Q2, exactly. This guy is a single vertex tree. This is our tree, right? Single vertex. Okay. So at this point, and what about the tight graph? The tight graph has nothing is tight, right? None of the two edges is tight. So I'm not going to draw it, right? Okay. So at this point in the tight graph, we can't grow the tree. We can't grow the matching. We can't, of course, don't have any odd cycles to shrink anymore, right? So we have nothing to do. The only thing we can do is DFS update. Exactly. So let's do step 21, DFS update. Okay, and let me draw this like this. This is Q2, this is V6. Okay, so the slacks are 2 minus 1 minus 0 is 1, and 4 minus 1 minus 0 is 3. So the minimum is 1. So we are going to increment for this guy Q2. Okay, and so the new solution will basically make the top edge tight and the bottom edge will still remain not tight, right? So this will become tight, and the dual variable has been incremented by +1, and here it is +1. There is something I want to mention here. What does Q2 really mean? I mean, Q2 corresponds to how many vertices in the original graph? 7 vertices. So it is not really a non-trivial tight cut, right? It is actually a trivial tight cut, right? 7 vertices on one side and 1 vertex on the other side. That is the same as looking at the cut corresponding to that isolated vertex on the other side, right? So basically Q2, the dual variable for Q2 is actually the same as the dual variable for V6 in this case, because we have reduced the graph to a 2 vertex graph. So actually when I say +1 for Q2, it is the same as incrementing for V6. So the V6 dual variable was at +1. So in this case, it's the same as saying that V6 is now going to be +2 and Q2 remains at 0 because Q2 doesn't mean anything. It is the same as V6. Okay. So that's the technicality that is going on here, which I realized when I was doing the example actually. Right. So this is the same as saying that V6 is at +2 and Q2 is the same as V6, right? I mean, it corresponds to the same variable as V6. It is not actually a different variable if you think about in the original graph what's going on, right? So this is yeah. Okay. So the dual variable for V6 has actually been incremented to +2, and that is fine because we have gotten all the way to a 2 vertex graph. Okay. All right. Okay. And now this top edge is actually a tight edge. So we will, okay, I shouldn't have done that. What I meant is, right, it is a tight edge, and this one I should have put as a dotted edge. Sorry. Okay. So now we have one tight edge and our right, and now we basically have an augmenting path because Q2 has an exposed vertex and is joined to another exposed vertex using a tight edge. So it is a single edge augmenting path. So in the next step, which is our last step actually, because the number of exposed nodes becomes 0, we will augment M prime, and the M prime will now become Q2V6. In particular, this is the edge corresponding to V5, V6. Okay, so the specific edge we are referring to is this one. Sorry. All right, you're right. Okay, you're right. Yeah, I missed a step. So we made an edge tight, and we would no. Wait a second. No, not really. So yeah, so basically what happens is whenever we look at the tree and a black node of the tree is connected to some vertex outside the tree, we immediately know that there is an augmenting path. So without extending the tree, we directly take that augmenting path and augment the matching. It's a technicality. You could potentially extend the tree and then say, hey, my tree has two exposed nodes, the root and another guy, and I will take the augmenting path. But we are skipping that step basically. Yeah. So actually, it's technically the way we're doing is fine. Yeah. Okay. All right. Did we, by the way, start recording? We did, right? We are recording. Good. Sometimes I forget. All right. So we have reached a situation where we have no M prime exposed vertices anymore. There do not exist any M prime exposed vertex. So at this point, we will be able to extend this matching M prime to a matching of the original graph by simply unshrinking the blossoms and keeping and extending it. Right? So let's just do that really quick. That will be the end of this particular example, and then we can spend some time on formalizing. Are you guys okay staying a bit longer today? Yeah? Okay, great. All right, so this is the edge V5, V6. So what I'm going to do is I'm just going to mark this edge in our previous graphs, right? So this is V5, V6, and maybe I should first unshrink Q2, right? So what happened? Yeah, yeah. So that is V5, V6, and if you take this, your matching will basically be the edges we had already marked earlier, V0, V2, and V1, V3, right? So we are tracing back. So right. So the plan is to now extend M prime to a perfect matching M of G by uh, repeatedly, recursively unshrinking blossoms. Right? So yeah, so we get V5, V6. So let me just write down the final matching. We've got this edge, and we have got yeah, in fact, yeah, so this edge Q2 V6 is really this edge here, and then we expand Q1. So what will happen then? We will get V4, V7, right? V5, V6 is here. So we'll take V4, V7, V0, V2, and V1, V3, right? Can we calculate the cost of this? Let's see. So we got V4, V7, V5, V6, V0, V1, sorry, V1, V3, and V0, V2, right? And that is a total of 4 plus 3, 7, plus 5 plus 6, 11, that is 18. Yeah. So we have a matching of cost 18, a perfect matching of cost 18 by simply doing this unshrinking business. Yeah. Um, yeah. So observe that the cost of this matching is equal to 18. I just want to draw the original graph again and observe the dual feasible solution. It should also be value 18, right? So we will also write down the dual feasible solution that we have at this point and check that this is actually a minimum cost perfect matching. Yeah. So the original graph looks like this. V0, V1, V2, V3, V4, V5, V6, V7. The matching we've got is V5, V6, V4, V7, V0, V2, and V1, V3. Let's put down the original costs. Okay, so it's 2, 3, 4, 4, 4, 6, 6, 8, 4, 5, 9. Okay. And what about our dual solution? So maybe I'll write down for the vertices first what the values are. Okay, so let's see. So notice that V6 has been incremented to +2. That we already have. And now let's go back to our previous steps, because basically we have the same values stored. We don't change those values from the last time that a blossom was shrunken, right? So if we go back, right, so in step 18 we shrunk a blossom, and we will just copy down the values from there. So it's plus 1.5 plus, wait a second, step 18, then we did a DFS update. Okay, sorry, that's not right. Yeah. Okay, so we shrunk the blossom Q2, and we should take the values from that point. So this is what I'm looking at. So V0 is +1, V1 is +1, V3 is +2, V2 is +3, right? Q1 corresponds to how many vertices? Q1 corresponds to V5, V4, V7. So that is going to be our odd cut. And the variable for that, the capital Y variable for that, is at +0.5. That was a blossom we did not unshrink in the algorithm. We only unshrunk at the end to get our matching, right? So it remained at 0.5. And what about V4, V5, and V7? Well, for that, we should go to the point where it was shrunken. So we'll take the values from there. So it was plus 1.5, plus 2.5, and plus 3.5. Okay, let us add these up. What do we get? So let us add the integers 3, 4, 5, 6, 7, 8, 9. Okay, and let's add up the fractions. 3.5 plus 2.5 is 6, 7.5, 8. That's a problem. What happened there? When did we do the blossom shrinking? We did it here. Oh, I see. The blossom shrinking was done here. So for the dual values, I should have looked at this point, right? I was looking here as usual, and that's not right. We should be looking at the last point, right? Then that was step 15, because this was at the end of step 14, right? So it would have been plus 0.5, plus 3.5, and plus 4.5. And those are the incorrect values here. So this is, yeah. Okay, and now let's put it back. So this is a plus 0.5. Yeah, so we are reading from here, right? This is the place we want to read from. 3.5 and 4.5. Now let's add up the fractions. 4.5, 3.5, plus 0.5 plus 0.5, that is 9. And the integers also add up to 9, so that's a total of 18. And the minimum cost perfect matching, the perfect matching that we have found is also 7 plus 11, 18. Okay, great. All right, so not a coincidence. It was supposed to be that way, right? The cost of the matching is 18, and the sum of the dual variables, both the small ones and the capital ones, for each vertex and for each cut, which is an odd cut. This is also equal to 18. Yeah. So we indeed have a min cost perfect matching. This implies that M is a min cost perfect matching. All right. So that's the algorithm. Yeah. Okay. Are there any questions or concerns at this point? We are still gonna make it a bit more formal and stuff. But I won't write down every single detail. I'll write down the main gist, and some of the subroutines you can try writing them on your own. Okay. Um, oh, by the way, one more thing I want to point out. Can we quickly draw the tide graph here? So let's continue. We have some space here. So V0, V1, V2, V3, 4, 5, 6, and 7. And let's draw the tide graph. So we have got naturally all the matching edges are going to be tight. Let me just put them. You can check that. Okay, what else? This guy is tight, V0, V1. V2, V4 is not tight, 3 plus point. Actually, it is because it is 3 plus 0.5 plus 0.5 from the odd cut because that edge belongs to the odd cut. So this is also a tight edge. 2 plus 0.5 plus 0.5 is not 4, so that V3, V4 is not a tight edge. 2 plus 3.5 plus 0.5, this is a tight edge because the cut includes this edge. 3.5, 0.5, 4, this is a tight edge. 3.5, 4.5 is 8, this is a tight edge. And the other one is not a tight edge. So I think this is it. Am I missing anything? Let me know, please. Those are all the tight edges, I believe. Let me just see if I have things drawn here. Yeah, I don't think I drew it. Okay, anyways. So I think these are all the tight edges. The matching is, these are the perfect matching edges that we've got. Sorry. Let's check the complementary slackness conditions, right? I mean, they should hold. Let's make sure that they are holding on this example. So what are the CS conditions? All the matching edges are tight edges. That is the easy CS condition. The tricky CS condition is that whenever a dual variable corresponding to a non-trivial odd cut is greater than 0, the matching edges, only one of them should be chosen from that particular cut. Right? The intersection of the matching, perfect matching, and the cut should be exactly 1. So if you look at this red colored, the only dual variable that we have set to greater than 0 is this particular dual variable, the capital Y variables I'm talking about. Right? So if you look at this odd cut, our matching is using exactly one edge from this odd cut. Now you might say that in this particular example, if you look at this tight graph, it's actually not possible to use more than one edge from this odd cut, right? Because if you want to use more than one, you will have to match all the three vertices V4, V5, and V7 outside the set, right? But V7 has nobody to match to. So in this particular example, this is something I realized in retrospect, but I didn't want to change the example, right? So in this example, of course, you take any perfect matching um, that meets the cut in exactly one edge, that will be a minimum cost perfect matching, right? Turns out there is only one, because V6 has to go to V5, V7 then has to go to V4 in this tight graph. Then of course V3 has to go to V1 and V2 has to go to V0. So it turns out that in this example, the tight graph actually has a unique perfect matching and it satisfies the second CS condition. However, you could have made this example more interesting, and I would suggest this as a try it yourself. So let's go back. So what you can do is, yeah, let me see, 7 plus this is 7, and so you can change this cost here, and you can make it you can make one more. Okay, so this is 9 6 4. Yeah, so if you look at this perfect matching, this edge, I'm matching this guy, I'm matching this guy, and I'm matching this guy. So I'm taking all these three edges and I have to take this edge, right? This would be a perfect matching which would meet the cut in all three edges, and that would violate the second CS condition, right? So I'm going to modify one cost, and I'm going to suggest you try the algorithm yourself after modifying this cost, right? So I want to make this a perfect matching of cost 18. So right now it's 6 plus 4, 10 plus 2, 12. So make this 6. Turn this into a cost 6 edge, okay? Now what happens is this matching that I've pointed out is 6 plus 6 plus 4 plus 2. That is again 18. Okay, so try this out. So I'm just going to put a to try it yourself problem. So so what happens if the cost of the edge V6 V7 is equal to 6 instead of 9? Okay, and try running the algorithm. Basically you want to try doing the same kind of things as much as possible and see how the algorithm is forced to change, how the execution is forced to change, right? So whenever you don't need to change it, you just keep it the same, right? But when you have to change it, well, then you do. And I'm hoping that when you look at the tight graph, you will have two different perfect matchings. One will meet the cut in three different edges, right? And the other one will meet the cut in exactly one edge, right? And the algorithm will give you the one which meets the cut in exactly one edge, right? Right. So yeah, so the way the algorithm is designed, it makes sure that the CS conditions, both of them are satisfied, which is why you will get a minimum cost perfect matching. Are there any questions or concerns at this point? All right, so in that case, now if not, let's go to a new page and let's write down let's formalize things a bit, but I won't write down every single detail. So formalizing. All right, so let's write down the main loop. At any point in time, we will have a derived graph G prime, which could be the same as the original graph. We will have derived costs C prime because we are also modifying the costs when we shrink the pseudonode, when we shrink a blossom. And we will have a matching at every point, M prime. Okay. So at any step, we will have a G prime, we will have a C prime, we will have a dual feasible solution, very important, Y bar, and we will have a matching. Notice that the tight graph can be computed by just looking at the G prime and the Y bar. So I'm not going to write down the tight graph. I will refer to the tight graph, but of course I mean that you compute it by looking at the G prime and Y bar. Okay. All right. So that is going to be, those are going to be the sort of input parameters for our loop, right? So let's write down the conditions. So what are the kind of steps we have? Let's see. we have extending the tree, we have augmenting the matching, we have shrinking the blossom, and we have expanding a pseudonode, which is unshrinking the blossom in some sense. Expand pseudonode. And we have, of course, a DFS update. Right? So let's write down the steps which, the conditions which lead to any of these things. So, well, so there are two ways to go about. I can basically just write down a bunch of cases. If this kind of edge exists, you do this. I prefer to write if-else statements, because if I can extend the tree, I would extend the tree. I would not shrink the pseudonode or shrink the blossom or something, right? So I'm going to write it down in that way. But most of the algorithms that I am presenting in this way, in the text, they actually write down just cases, because you could actually do whatever you like and the algorithm still works. To me, it just makes intuitively more sense to extend the tree if I can extend the tree, or augment the matching if I can augment the matching. Right? So if there exists an edge UV in the tight graph, E tight, such that oh, we should also have a tree at every point. Sorry, I should have included that. At every point, we also have a tree. We have an M and a tree, right? And the tree is always a subset of subgraph of the tight graph. All right. So if there is an edge in the tight graph such that U is a black vertex of the tree, recall that U of T are the black nodes and W of T are the white nodes of the tree. And the convention is that the root is always a black node, right? So then everything is defined clearly. So if the one end is in the black nodes of the tree and the other end is not a vertex of the tree at all, okay? In this case, well, there are two possibilities. Either this other vertex V is a matched vertex or it is an exposed vertex, right? So if this vertex V is M prime exposed, then we have basically found an augmenting path, right? So in that case, the step we want to do is augment M prime. Okay, I won't write down the subroutine. You know how to augment the matching. So we augment the matching, and at this point we want to check if the new matching is no, there are no exposed vertices after augmenting. Then we just extend it to a perfect matching in the original graph, and we return that perfect matching. Otherwise, we will just change the tree to a new exposed vertex. Right? So if M prime, if there do not exist any M prime exposed vertices in G prime, then I'm just going to write it here. Extend M prime to a perfect matching M of G and return this perfect matching with the dual solution that you have, right? Return M y bar and capital Y bar, right? Else, we have an M prime exposed vertex, and right. So in this case, we simply reset the tree to some exposed vertex with no edges. Right. The other possibility is if the vertex is not exposed, then what do? Extend the tree. So in this case, we simply extend the tree T. Okay, and I won't write down what that means. You all know what that means. Great. Okay, so that is the case when you have this kind of an edge. Okay, so what is the other possibility? Otherwise, well, maybe you have an edge joining two black nodes of the tree. Okay, that's another kind of edge that we care about. So if there exists an edge UV in the tight graph such that both U and V are black nodes of the tree, then what do? Shrink this blossom. Exactly. So in this case, we shrink blossom Q, where Q is the unique cycle, which will be an odd cycle in the tree plus the edge UV. Right? Okay. And when you shrink the blossom, I'll just point out that this will update a bunch of things. It will update the matching. It will update the tree. It will update the graph, and in particular, we will set y bar for the new Q. Right. So this pseudonode, its dual variable will be set to 0. Right. Great. All right. So this is the shrinking blossom subroutine, which I'm not going to expand out. Okay. So if we don't have this guy, what else do we look at? Maybe we have a white pseudonode. Right. If we have a white pseudonode, we will basically expand it. Right? Otherwise, there exists a pseudonode, let's say Q, little q. There exists a pseudonode Q among the white vertices of the tree, such that its dual variable has reached 0. Right? If it doesn't reach 0, then we can just do a dual update. Right? So the y bar Q has reached 0. In this case, we simply expand the expand the pseudonode Q to, I'll just say expand it. Right? And this will also update things, right? This will update things in the same way as the previous step, but not in the same way, but it will update all of those things. It will change the tree as we discussed. You take the even length path between those two vertices. You change the matching. You update the costs. You update your graph, and that's it, right? All right. Oh, and of course, the dual feasible solution will also update based on your previous step where you did the shrinking, right? All right. When I say y bar, I mean both y bar and capital Y bar. Okay. All right. Hmm. In fact, perhaps it is not right to say that the y bar is updated, because it's not actually updated. It's just what we had before. I'm going to actually remove this because it's confusing, I think. Because the dual update only occurs when we do a dual update. The only exception is these variables. right, which we set to 0 for the small nodes, right, which basically is, even that is not a real update. Even that is basically the capital Y bar that corresponded to that small Y bar in the new graph, right, and the capital Y bars were all set to 0 originally, right? So yeah, so if none of these things are possible, in that case we do a dual update, right? And because we are assuming that the original graph has a perfect matching, one of these cases will always happen, right? We should be able to do this, right? In particular, the dual update will not fail because the beta that you compute will necessarily be greater than 0, and that is because we are assuming that the original graph is a perfect matching. So you either will have those kinds of edges in the tight graph, or you will have some pseudonode that is a white colored pseudonode, because if none of those things happen, then the white colored vertices will correspond to a touch set in the original graph, right? That's basically the reason you won't get stuck. So basically now none of the above apply. And at this point, we do an update on the dual feasible solution, right? I will just write down by computing beta as the minimum of beta 1, beta 2, and beta 3 as we discussed in the last lecture. Okay, and then you add the beta to the black nodes and you subtract the beta from the white nodes. Because the number of black nodes is strictly greater than the number of white nodes, you will have an improvement. Yeah. Okay, the only thing we need to now do is initialize things. That's boring stuff. So G prime is simply the original graph G, C prime is simply the original cost C in the beginning. And what about Y bar? For the Y bar for the vertices, we simply set it to um, half of the minimum cost, right? Minimum cost among all edges. And this is for each vertex. And capital Y bar is simply the 0 vector. And the matching M, you could start with the empty matching, and the tree could be just any exposed vertex, where R is just any vertex, right? Assuming that the graph has at least 2 vertices. Yeah. Okay. Good. So there are a bunch of subroutines. I'll just underline them and not write them down. Oh, this is also fine. Extend the tree, expand the pseudonode, and update the dual feasible solution and shrink the blossom. Right. So do it yourself. Write down the subroutines, which are basically listed here. Okay. All right. So that's formalizing the algorithm. Let us quickly discuss the runtime. So I'll just state the theorem, and we will discuss it briefly. So this is known as Edmonds Blossom Algorithm, the cost version. Right? So basically, they're both known as Blossom Algorithm, and I don't really know how to distinguish. So Edmonds Blossom Algorithm, cost version, um, returns a min cost perfect matching, um, and dual feasible solution M and Y bar that satisfy the CS conditions. And the thing that I want to discuss is the time complexity is order n square. Okay, so let me see. Yeah, so the correctness, it's a bit tedious. Basically, the only thing you need to keep track of is that when you shrink a blossom, um, if you solve the problem for G prime, C prime, your new shrunken graph and the new costs, then and you get a solution for that, and you make sure that the dual variable for the shrunken vertex, let's say the shrunken vertex is q, little q, right? If you make sure that the dual variable corresponding to little q is strictly greater than 0, then it implies that you've actually solved the original problem, because you can just extend this matching m prime to a matching in the previous graph, and you will have solved it for that. Of course, you can do this recursively and go back all the way to the original graph, right? So you need to prove that at any step when you go from GC to G prime C prime, solving G prime C prime implies that you have solved G comma C, right? So I'll just summarize the main point, and the proof is it's basically making sure that the complementary slackness conditions will hold even in the previous graph, right? And that's not difficult. So basically, um, so for the correctness, the key point is the following. Let's say you go from G comma C to G prime comma C prime, where this is a shrink blossom step. The other steps are actually not that, I mean, they are actually much more straightforward. They are similar to the Hungarian algorithm. The main big difference is the shrinking blossom step. So then the claim is that suppose you solve G prime C prime. Let's say we shrink blossom Q to a single vertex Q, and the y bar value for this node, this pseudonode, is greater than equal to 0. Then this solution extends to a solution for G comma C. And the key point is, how do you prove this? It's simply showing that if the CS conditions hold for G prime C prime, they will also hold for G comma C. And it's just tedious details, right? So in this algorithm, if you reach a point, so there are implicit assumptions here. You shrink the blossom, then solving it on the smaller one, you will solve it on the original one. So essentially, one needs to show that if the CS conditions hold for the smaller instance, then they also hold for the bigger instance. And it's a lot of bookkeeping. Okay, so I won't write down this proof. All right. Yeah. And and expanding the pseudonodes back to the blossoms, that's even easier to see actually. So I won't even mention that point. Right. So if you expand it, you already had a certain partial solution, and you're simply going back to that partial solution, right? So that doesn't change things a lot really. The point I want to discuss is the time complexity. Okay, so what are the kinds of steps we have? We have these steps here. So observe that every time we augment the matching, the number of exposed vertices in the graph G prime, our current graph G prime, reduces. And in particular, the number of exposed vertices will never increase. It has to just keep going down, or it can remain the same. In all other steps, it will remain the same, but when you do an augmentation, it will reduce. Right? So what we'll do is we'll look at what happens between two augmentation steps. Okay, so the number of yeah, so the number of augmentation matching augmentation steps is order of n, since number of exposed vertices, m prime exposed vertices, never increases during the algorithm, right? It's always monotonically decreasing. So now the question is, how many other steps between two augmentation steps, right? So what are the other steps we care about? We have extending a tree, shrinking a blossom, expanding a pseudonode, and DFS update, right? So let's look at these. So there is DFS update, tree extension, shrink blossom, and expand pseudonode. How many of these can happen? So observe that you never do dual DFS updates consecutively. If you do a DFS update, in the next step, you will be doing one of these three steps. So we are looking at between two augmentation steps, right? So if you do a DFS update, at the next step, you will never do DFS update again because you updated it as much as you could, right? So you have basically one of the edges will become tight, or one of the pseudonodes, its value will come down to 0. So the next time you compute beta, the beta will be 0, right? Because you increased it as much as you could under the current scenario, right? So you never do two consecutive DFS update steps, right? So which means after a DFS update step, if you are not going to do an augmentation, you will be doing one of these three steps. So that means that we just need to bound the number of times these three steps occur. If we can bound the number of times these three steps occur, then we are done. Do you guys agree? Okay. So this one, we don't care because um, after DFS update, some other step must occur necessarily. In other words, it suffices to bound how many times the other three things can happen. Okay. All right. So let's see. So how many times can you shrink blossoms? If you've gotten a matching and you keep shrinking blossoms, right? How many times can you do that? There's a there's a tricky point here, right? You guys see there's one issue here that we need to resolve. We have the shrinking blossom thing, and we also have the expanding pseudonode thing. So how do we resolve that? Okay. Um, but there is something even better that happens. I claim that if you look at, so, all right, let me see. So if you are looking at supposing you have a particular matching, right? We are looking at a matching augmentation has occurred, and then the next matching augmentation is occurring sometime later. We are looking at these steps. So in fact, you are expanding the pseudonodes that are white in color, right? However, when you are constructing the tree, the new pseudonodes are always going to be black, right? When do you shrink a blossom? You shrink a blossom when you see um, an edge joining two black nodes. When you shrink that blossom, the new vertex little q will become a black node in your tree, right? So whenever you shrink a blossom, it becomes a black node. So which means that the pseudonode expansions that you are doing, they correspond to the blossoms you shrunk in an earlier step before this augmentation. So in the same tree construction, you never shrink and unshrink the same blossom. So these blossoms that you are expanding, these pseudonodes that you are expanding, they are coming from a previous time when you had done some shrinking. You can go back to this example and check that when you expanded the blossom Q, that was not in the same, it became a white node, whereas when you shrunk it, it was a black node. So the tree had actually changed, and the tree change occurs only when you augment the matching, right? Only when you augment the matching, you say that, okay, now I'm going to assign an arbitrary node, arbitrary exposed vertex as my root, right? So actually the shrinkings and expansions are not contradicting each other. They are separate sets of vertices. Yeah. So the point I want to make here is the shrunken blossoms during any tree construction. So when I say tree construction, I mean within a certain augmentation, between two augmentations of the matching, right? Because between two augmentations, you never reset the tree. You keep the tree as it is. The only time you reset the tree is when you augment the matching, and then you say, hey, now I'm going to reset to some exposed vertex arbitrarily. Right? So during any tree, let's say, yeah, shrunken blossoms during any tree, right? Maybe let me rephrase it. Shrunken blossoms between two augmentations um, are distinct from the expanded pseudonodes, right? So they are not really contradicting each other. So you will not get into this infinite loop situation where you keep shrinking and expanding the same thing, right? All right. Now, if you think about these two steps independently, well, how many times can you shrink the blossoms? Well, you will keep shrinking. Eventually, you will reach a graph with just two vertices, right? So you are bounded by order n. So this is order n. And the same with expanding pseudonodes, right? Because how many times can you keep expanding pseudonodes given that these are dealing with different sets of vertices, the shrinking and the expansions, right? You can only expand as many times as the number of vertices in the original graph. So this is also order n. And what about tree extensions? Well, the tree can't be bigger than the number of vertices in the graph, so this is also order n, right? So between any two augmentation steps, all of these are linearly bounded. And so that implies that the final running time is order n square. Yeah. Okay. All right. So I think we are quite 6:30 already. Let me just make one point that you see the correctness of the algorithm, which we did not prove in detail. I just sketched it, and there are details that are missing. However, the correctness implies Edmonds perfect matching polytope theorem because you find a perfect matching and a dual feasible solution that satisfies the CS conditions. In particular, that implies that your IP, your LP relaxation, which is Edmonds LP relaxation, and the dual, they all have the same value, right? So that in particular means that your minimum cost perfect matching is the same value as the dual feasible solution. And that means that the LP is exactly capturing the perfect matching polytope. So, I mean, let me just go back to this theorem statement that I wrote earlier. Yes, I think we wrote it somewhere here. No, okay, anyways, I don't think we wrote it here. Yeah, let me just open this. Yeah, and let me change the screen I'm sharing. Okay. Yeah, I didn't want to write down the whole theorem again. Yeah, so this is the Edmonds perfect matching polytope theorem. So there are two parts. We haven't actually proved the first part, but let's look at the second part. So if the graph has a perfect matching, which we are assuming, otherwise we would just not run the algorithm, right? So if the graph has a perfect matching, then the minimum cost of a perfect matching is equal to the optimal value of Edmonds LP, right? So it's proving this part. It's not actually proving that the polytope is the same. It's just proving that the optimal value of the LP that Edmonds gave is the same as the minimum cost of a perfect matching. That's the part it is proving, right? Because we found a dual with the same value. So the primal also has the same value, which is the minimum cost of the perfect matching, right? So this proves the second part of theorem 5.13. It doesn't prove the first part. It doesn't say that the graph has a perfect matching if and only if the LP has a feasible solution. But that's not too difficult either. I might try to put that on your assignment with breaking it into parts or whatever. Yeah. So it does prove the second part. So that's the thing I wanted to state. So, all right. So observe that theorem 5.16 implies the second part of Edmonds perfect matching polytope theorem. Right. Okay. So I think that's all I want to say about matching algorithms. We have seen both the cardinality and cost versions for bipartite as well as non-bipartite graphs. So next week, we will either continue discussing some primal dual algorithms or we will look at some applications of duality. But I am going to omit matroids because we really don't have time to do justice to that subject. So I would rather not do a poor job at that part. Rather, I would rather just focus on duality, right? Because also it's more connected to everything we have been doing. So matroids will require a complete gear shift, and I think it will just not be enough time. Yeah. Okay, so that's all for today. You guys have any questions? All good? All right, so sorry for going over time, but yeah, have a good long weekend, and I'll see you guys on Monday. And I'll stop recording now. Nobody's in the call, so it doesn't matter.